You know how a single word, like play, can mean totally different things? It could mean playing a guitar, playing a game, or playing a role in a movie? Well, in the world of programming, we have this exact same idea, and it's called polymorphism. It's this amazing concept where one name can truly have many forms, and we're going to break down exactly how it works.
And we're going to start with a bit of a puzzle. A single line of code that, if you're new to this, might look a little weird. Shape S equals new circle. Okay, so we're making a circle, but we're calling it a shape? What's the deal with that? By the time we're done here, you'll not only get it, but you'll see why it's such a game changer. All right, so to crack this puzzle, we got to start with a foundation. We need to understand what we even mean by shape in the first place. Think of it as a universal blueprint.
Now, this shape class, it isn't a real thing. You can't see it or touch it. It's more of an idea, a set of rules. It basically says, look, if you want to be called a shape in my world, there are certain things you absolutely must be able to do. It tells you what needs to be done, but it doesn't care how you do it.
And the fancy term for this kind of blueprint is an abstract base class. It's really just a contract. It sets up a common language for a whole family of objects, making sure they all play by the same rules, even if they all look and act differently.
So what's in our shape contract? Well, there are two big rules. Rule number one, every single shape has to know how to calculate area. It needs to figure out its own size. Rule number two, every shape must know how to draw itself. The blueprint demands these abilities, but it leaves the nitty-gritty details up to the individual shapes.
Okay, so we've got the blueprint. Now for the fun part. It's time to actually use it to build something real. We're going to take that abstract idea and bring some actual concrete shapes to life.
And this is where our circle class and our rectangle class show up. They both raise their hands and say, yep, we'll follow the shape blueprint. They become subclasses of shape, which just means they're specialized, real-world versions of that abstract idea. But here's the cool part. Each one follows the rules in its own unique way. A circle, well, it needs a radius to calculate its area using pi times r squared. A rectangle, it needs a width and a height. See? They both fulfill the calculate area contract, but the how, the actual math, is completely different because it's tailored to what they are. And now, we have all the pieces. We've got our abstract blueprint and our concrete shapes that follow its rules. It's time to go back to our original mystery and finally see what's really going on. This quote really hits the nail on the head. When we write shape S equals new circle, we're using a general, universal label, shape, to point to a very specific object, a circle. And this lets us handle all sorts of different shapes in one uniform way, which makes our code so much cleaner. Think of it like this. You have a variable, S, that's basically a box with a label on it that says shape. But the arrow pointing out of that box doesn't go to some vague idea of a shape. No, it points to a very real, very specific circle object that's sitting in the computer's memory. The label is general, but the thing it's pointing to is concrete. So when we tell S to draw, how does it know to draw a circle and not a rectangle? This is the magic trick. It's called dynamic method dispatch. First, when you compile the code, the compiler just does a quick check. It says, okay, S is a shape. Does the shape blueprint have a draw method? Yes, it does. Check. But the real decision happens later, at runtime. The program actually runs, looks at what S is pointing to, and sees, oh, that's a circle. And only then does it call the draw method from the circle class. The right code gets picked at the very last second. So that's the how. It's a pretty cool trick, right? But the why? That's where things get really powerful. Why does this whole magic trick matter so much when you're building software? For one, it gives you incredible flexibility. Imagine tomorrow your boss says, hey, we need to add triangles to our program. No problem. You just create a new triangle class, make it follow the shape blueprint, and guess what? All your old code that was written to handle shapes will instantly know how to handle triangles. You don't have to change a thing. Second, code reusability. This is huge. You can write one function, just one, that does something like center a shape on the screen. And because that function works with the general shape type, it can now center a circle, a rectangle, a triangle, or any other crazy shape you invent down the road. You write the code once and it works for everything. And third, you get this amazing dynamic behavior. You can have a whole list of different shapes, a circle, a rectangle, another circle, and you can just loop through them and say draw to each one. The program automatically figures out which draw method to call for each object on the fly. It's incredibly adaptive. So when you put it all together,
Polymorphism lets developers build these really complex systems that are so much cleaner, way easier to update, and a lot simpler to expand. It's not just a trick, it's a foundational tool for building software that can actually grow and adapt over time.
So, we've seen how one name, shape, can command many different forms. This idea, this principle of having a single, simple interface that can control all sorts of different implementations, that's a powerful way of thinking that goes way beyond just code. It really makes you wonder, doesn't it? How does this change the way you think about building things?